So yesterday we talked about weak acid equilibrium problems in the context of weak acid titrations. And right now we're really isolating just to the weak acid behavior and predicting the amount of ion, a hydronium H positive ion present to then quantify the pH of a solution. And these problems really resemble unit 7 equilibrium problems because it is equilibrium. It's a weak acid that's in equilibrium, and we have to use an ice table to predict the amount of acid concentration at equilibrium. And so therefore we got three types of problems. We were able to go through a practice round with the first type of problem where you were given Ka and initial Ha acid concentration, and then you had to figure out what the equilibrium concentration acid was, the H plus proton. Okay, and you were able to go through a practice round on your own, okay, with methanoic acid, to which I shortened to meth. Okay, then we introduced the second type of problem where you're given Ka and pH at equilibrium. So from that pH at equilibrium, you can find the concentration of H at equilibrium to calculate the initial H acid concentration. Okay, and so that's our first warm up to see if you could do it on your own. So out of curiosity, what did you guys get for this first one? You were given that pH is equal to 2.5. So hopefully, guys, you have good news to share with us?
Oh no, I just right before you said that, I just like randomly blurted out 2.5. I'm such a
Wow, look at you being my other brain cell. Good job.
one of two.
You'd be like,
What?
Say other.
that is true.
I just finished the brain cell.
Why are you in my class?
I don't want to.
Okay. So from the pH of this prompt, you could find the H equilibrium concentration by doing 10 to the negative pH. So you should have found that the concentration was 3.16 times 10 to the negative third molarity. And then you would have set up an ice table. I'm going to make it short and do H sit and plus water, because we're just isolating this to a hydrolysis reaction with water. Goes to deprotonated sit and with a minus charge and H3O plus acid. You would have set up your ice table, okay? And of course, water doesn't matter here. And you would have figured out from the information given above.
Wait, were we supposed to know what citric the formula for citric acid is?
No, you don't have to. And then what you would have gotten was, oh shoot, no one told me to remind to give you the Ka. Don't worry, you would have, if you could get this far, you'll be fine, because they'll always give you the Ka. So what you should have realized is if you were able to determine the equilibrium concentration of the acid from the pH of the solution. So what you do is you put it in to the table, and that means stoichiometrically speaking, you are adding 3.16 change, 10 to the negative 3, which means for the other ion, you are also getting a 3.16 blah, blah, blah. So I'm just going to do 3.16 times 10 to the negative 3 here, which means stoichiometrically, you're in a 1-to-1-to-1 ratio because this is a monoprotic acid. This is a 1 H proton transition acid, or yeah. And what you get is that whatever your initial value for H that you're trying to find, it's going to be minus stoichiometrically a 1-to-1 ratio. So minus 1 times 3.16 times 10 to the negative third, which means it becomes X minus 3.16 times 10 to the negative third for predicting the equilibrium concentration of your original acid. All right. Here we cannot use that 5% assumption rule because you don't know if it's negligible. You don't know if your initial concentration is 1,000 times greater than your Ka. And you would have been given the Ka. You could have also looked it up in your notes on previous pages. I did put a bunch of Kas in a table, but the Ka for this would have been, or is, not would have, it is.
How did you know that it's like the equation?
The equation?
Yeah, is HC.
H citrate. I'm just trying to show that it's protonated citric acid.
Oh.
That's all I'm showing. So the Ka is for protonated citric acid is 7.1 times 10 to the negative fourth. So then what you would do is you simply plug in to the K expression your equilibrium values that you determine. So 3.16 times 10 to the negative 3 squared, because it's the ion H3O plus times the citric deprotonated ion, okay, all over the concentration of H citric acid, where you have X minus 3.16 times 10 to the negative third. And when you solve for X, what you would have gotten is that X equals 0.017 molarity, 0.017. And that's how you would solve this problem. And why can I not write this in a way that is legible? 0.017 molarity. And so basically it's just algebra. The hardest part is just making sure that you're acknowledging the stoichiometric changes and making sure that you recognize the information that you have. A lot of people, when they read this, they say, oh my gosh, I don't have enough information. But the pH of the solution once mixed is the information that you need. It gives you that second piece to figure out the third. They will never give you a problem that has more than one unknown variable. You might just have to work a little bit backwards. Okay. So, any questions with this, Jaden?
So would KA be given to us?
Yes, always, always. And KA, I did give you a bunch of tables in your notes so that when you're working through problems, you can find it. Okay. But it would always be provided some way or another. So for the next problem, the third type, okay, it's the dream type. It's the plug and chug type. It's, I give you initial and equilibrium. All you have to do is solve for KA. So for this problem that you were given to warm up with, okay, you would have simply, you have your ascorbic acid. So I just did I just did H plus H2O, because honestly, the formula doesn't matter as much at this point, as long as I know it's a monoprotic acid transforming. And then I got ask to the negative sign.
There's 2 hydrogens.
Oh, you were. No, because the ascorbic acid will only lose one. It's a polyatomic that includes one of those H's as part of the polyatomic. So it won't lose the other one.
Am I supposed to just like memorize that this one doesn't?
This is a way harder problem than you would be given in an AP, because it uses a far more complicated molecule than you would be asked to deal with. And then we got H3O plus. So all you would do is set up your ice table. And you were told that you started with 0.100. And whatever your pH was, which was pH of 3, you would simply do 10 to the negative pH to figure out your equilibrium values. And then from there, you would do your stoichiometric change, right? You would change accordingly. And you would find then when you plug in your values, what did you find for Ka? Did anyone find this Ka? Is anyone confused about just how to fill in the table given these 2 data points? Just didn't have time? Totally fine. Do we feel comfortable with this idea of, if I have been given the pH of the solution, that does reveal to me my equilibrium concentration of the acid, and then I can just stoichiometrically figure out the change? So whatever this value is, that's plus 10 to the negative pH. This is going to be plus 10 to the negative pH. This is going to be 10 to the negative pH as well, because it's a 1-to-1-to-1 ratio. Okay. And this is going to be.
Wait, how do we know if the acid is at equilibrium?
The assumption is that you've mixed it and it has reached equilibrium. Like the assumption is that your solution has established its own equilibrium, because all solutions are in work.
How do we know that it's talking about the H3O acid and not the ascorbic acid?
Well, the ascorbic acid is releasing the H plus, which was carried by the water to create H3O plus. Hydronium ion H3O plus is just like saying the acid that's been donated from the original, more complex molecule. Okay, so then the change here would be 10 to the negative pH, but subtract it. So it would be 0.1 minus 10 to the negative pH value. And then you would simply plug in whatever that number is into Ka expression. So it'd become 10 to the negative pH value squared all over 0.1 minus 10 to the negative pH value, which should have given you a value of approximately 1.0 times 10 to the negative fifth, no units, because K values, capital K values have no units. Little k, unit 5, kinetics definitely has a unit. Big K, equilibrium, not important. So that's for weak acids. Now we do the same thing with a weak base. And all that really changes for us is that sometimes we're given information in the acid perspective. And so we have to use one of those relationships between acid and base and water to get to the base perspective. So it's just a couple extra finishing calculations, but it's the same principle. So do you guys just need a second to write?
Nice.
Let's move on to weak base calculations. Essentially, this similar replica, but just with maybe a couple extra conversions. So here again, we see partial ionization with a weak base. So of course, we're going to assume a reverse reaction, and thus the process is in equilibrium. And we're going to have the same three types of problems. We're going to have a problem where we're given a variety of the 2 out of the 3 variables. But the big thing to remember is with weak base calculations, you really want to remind yourself of a couple things, that Kw is equal to Ka times Kb, and that pH is equal to 14 minus POH. Because oftentimes with weak base calculations, we're given the Ka of the species we're analyzing from the acidic point of view, but we need to quantify it as a base. So we have to convert the Ka to Kb for that specific species. In addition, we often ask for the pH of the solution in the end, not the POH. So we often have to convert our POH that we quantify into a pH terminology. Okay? So, problem type 1. Calculate the OH at equilibrium given the Ka or Kb, because sometimes what they give you is the Ka instead of directly giving you the Kb, and the initial base. Don't forget, we do have for this type of problem the percent ionization rule of 5%, where we consume negligible if your initial base is 1,000 times greater than your Kb value. We can still apply that here, just from a base perspective. So there's a lot of kind of side piece instructions. Let's just kind of go through it. It's easiest. Okay, of course. So here we're told that we have methylamine, okay? And we have the Kb of methylamine given to us, and we have the pH of the final solution. And we're asked to determine the OH, the base ion produced. So what we have told to us is we know that Kb is equal to 4.4 times 10 to the negative 4th. We know that the initial amount is 0.5. Initial, okay, is equal to 0.5. So we can say here pretty safely that we can apply the 5% rule. 5% negligible, is applied. I'm just gonna do a check mark, because it's definitely 1,000 times greater. The initial amount of base, and maybe I don't even want to write OH. Maybe I just want to write base, because the base produces the OH, so I should be more careful. Okay, is 5%. Okay, but basically negligible amount, not significant enough for us to worry about in our calculations. The initial concentration is over 1,000 times greater than the Kb. Looking just at the power. Okay, so then we set up our ice table. So we say, I'm going to call it, I'm just going to shorten it to meth again. So here we have meth base, okay, reacts with a hydrolysis. Again, we're going to isolate the base behavior by just doing a hydrolysis reaction, okay? And we'll get to, by the way, acid base in a second, but we're just going to isolate first, characterizing the base nature, okay? And it gets to protonated meth, with a positive charge and produces OH minus. Because here it accepts the H proton from the water acting as the acid now, and now leaving it with just a hydroxide ion. Okay, so what we do then is just like normal, we set up an ice table. Okay. And then of course, water doesn't matter because water is a liquid and we can't do anything with liquids in our K equilibrium expression. And so what we know is from our problem, we have an initial base amount of 0.5 and we have a KB of 4.4 times 10 to the negative fourth. So initially we have no ions, but we know stoichiometrically speaking, the change should be positive X. This is a monoprotic, not even a monoprotic, a monohydroxide, okay? A monohydroxide base. So whatever the change is, it's going to be a 1-to-1 ratio of change, okay? So then what we get is 0.5 minus X for equilibrium concentrations, X and X. Now, we've already said that we're at the 5% ionization rule. Our initial base is 1,000 times greater than our KB, which is like saying our initial amount is 1,000 times greater than the ability to produce an ion itself. So we're basically going to treat this change in the initial amount to be negligible. So then when we do is we set up our KB, we would get, okay, that the KB is equal to 4.4 times 10 to the negative fourth. I'm really not sure what you're talking about right now. 4.4 times 10 to the negative fourth is definitely not chemistry. Equals to the two ions multiplied by one another. So X squared for the equilibrium concentrations of each ion produced and over 0.5, which by the way will give us an X equal to 0.0148 molarity. And if I were to ask you to find the pH, just as a little bonus, if I were to ask you to find the pH of the solution, you cannot do that directly from that concentration value because you have a hydroxide base concentration. So what you would do is you would actually find POH first, which would give you 1.829 based off of your base value for here. This is your OH concentration at equilibrium. And then what you would do is you would use the additional equation relating pH and POH to say that pH is equal to 14 minus 1.829, giving us a pH in the basic range, which would make sense because we're making base, of 12.17 if I wanted you to take it all the way to the end. So why don't you try the next problem on your own? Yes, Jaden? Because I did negative log of the concentration at equilibrium of the base, particularly the base ion, not just the original base, but the ion produced, the OH minus. All right, go ahead and try the problem below. Okay, so here's like the setup of the problem. And when I gave you the Ka, what you have to do is you have to solve for the Kb, which is defining from the base perspective, how likely going in the base direction am I going to produce OH minus. That Ka value is telling me how likely I'm going in the acid direction. HCN producing H2O acid, because here the water is acting as an acid. Okay. So for this problem, once you get this set up, what you see is that you start plugging in. So I would have found, given my Ka, I would have found that my Kb is equal to 2.04 times 10 to the negative fifth, given my Ka, and Kw is 1.00 times 10 to the negative 14th, because I'm assuming room temperature unless otherwise told. So then what I get is I'm told at the beginning of the problem, I have 0.2 molar base. And I initially have no, okay, ions produced. And then my change is, okay, negative X, positive X, positive X. Stoichiometrically speaking, I have a certain amount of change, okay? And so then my equilibrium concentration is 0.2 minus X, X, and X. Now here I see that my concentration is definitely 1,000 times greater than my KB, my initial concentration. So I'm going to apply the negligibility rule. 5% ionization, check. And so then what I do is using my KB,
Wait, don't we already know? Oh, that's the KB.
I plug in my KB expression, 2.04 times 10 to the negative fifth. I plug in X squared all over 0.2, giving me an X, which is equal to the concentration of OH minus at equilibrium of 0.00202, 0.00202 molarity. Once I have that, then what I get is that my POH is equal to the negative log of this value, which is going to be POH, negative log of this. And then all I do is pH is equal to 14 minus POH if I asked you to also get me the pH. And I would have gotten a value of 11.31. You were just asked to figure out the concentration of OH minus, but in your AP problems, they very rarely have you stop here. They have you carry it all the way through to your pH value. And it makes sense that you have a high pH because you are working with a base producing hydroxide ion solution. Oh, perfect. The first one wasn't. This is a really good example of an AP problem. This is a great example of an FRQ portion. Okay. So now problem type 2, it's going to mimic the other problem type 2. Now we have a different combo of two knowns and one unknown. And here, okay, we again never can use percent ionization negligible rule, negligible assumption. Because here we have to calculate the initial. So we don't know if it's negligible or not. We don't know if it's 1,000 times greater. So we cannot do any of that shortcut stuff. So for this sample problem here, this is problem type 2. This is where we have two different variables now. Now we're given Ka or Kb and the pH or the equilibrium concentration, but we're not given the initial. So we can't assume anything about the initial's value compared to Kb. So what we have here then is we are told in this problem that the pH is 10.50. But wait, I'm from the base perspective. So what can I do? If this is the pH at equilibrium, that means I can say that 14 minus the POH at equilibrium, I can figure out, which is going to be equal, okay? Well, if I rearrange it, let me put it actually in a way where I can rearrange it so that I can say that the POH at equilibrium is equal to 14 minus pH at equilibrium. So I get that POH at equilibrium is equal to 14 minus 10.5. So I get that it's equal to 3.50. And based off of that at equilibrium POH value, I get that the concentration of my hydroxide ion at equilibrium is equal to 10 to the negative POH, which is going to be equal to here in my previous problems, I got 3.16.
No, the sig figs for POH.
Oh, POH? No, it would be, it's still in the logarithmic.
Oh, yeah.
So this would be the concentration of your hydroxide ion produced at equilibrium is going to be 3.16 times 10 to the negative fourth molarity. So once I figure that out, now I need to figure out what Kb is because apparently that's given to me. So the Kb for NH3 would be 1.78 times 10 to the negative fifth, which by the way, you could solve by doing Kw over the Ka for NH4 plus, the acidic form of NH3. You could also do it that way. It might be given to you as a Ka, and you had to calculate what the Kb was. That might be their way of giving it to you. So then we set up our ice table and we say, okay, so I have NH3 base being protonated by, this time our water is acidic, hydrolysis reaction in a weak base equilibrium reaction to produce acidic ammonium and basic hydroxide ion, or at least protonated ammonium. Okay, so ICE, we don't know what the initial of NH3 is. That's the whole thing we're solving for. But we do know what the equilibrium concentration is for hydroxide, 3.16 times 10 to the negative fourth, right? And if we know that whatever change occurs, it's stoichiometrically connected to the other species, then that means we've also gained 3.16 times 10 to the negative fourth. So a concentration of 3.16 times 10 to the negative fourth at equilibrium for my protonated ammonium, which is, and then we don't pay attention to the liquid water. And we know that my ammonia base, my weak base ammonia, is going to be minus the stoichiometric 1 to 1 to 1 of 3.6, 16 times 10 to the negative fourth. And so I get x minus 3.16 times 10 to the negative fourth. Okay.
When do we know to use like
the 5% rule?
That number.
That.
How did you even get the number?
So this number 3.16 comes from me figuring out the equilibrium concentration of hydroxide ion based off of the equilibrium pH.
Yeah, that makes sense.
Okay.
But when do we know when to use that number instead of X?
Well, we use that number where it fits in the table. So it fits in the table as the equilibrium concentration of OH. That's where it fits according to the table information. It is our value of OH concentration at equilibrium. So we put it into the table in that slot. And then that reveals to us the change, because we assume that no hydroxide base has been made until things have mixed. So initially, that ion is always 0 for the most part. There are a couple cases in AP problems where they actually have you do Le Chatelier shifts with these, where you start with a condition and then you change that condition. But right now, you're starting real basic. Literally. Thank you. I saw Hayden to his demise chuckle. So then what you do is you plug it into KB. So you say KB is equal to 1.78 times 10 to the negative fifth, which is equal to my ion concentrations, my product ions. So 3.16 times 10 to the negative fourth, they just happen to be squared because it's a 1-to-1 ratio, all over x minus 3.16 times 10 to the negative fourth. And you would get that x is equal, okay, to, there's my math, 0.0059 molarity. Okay. And I could ask you then this, by the way, well, no, I wouldn't ask you pH because it's the initial concentration. So you're done. That is the initial concentration of NH3 base, weak base, ammonia. Okay, try the next one on your own. So for this one, what you should have noticed is that you were given POA or pH. So you had to figure out what the POH was. And this is at equilibrium values. At equilibrium values. So you would have figured out that the POH is equal to 14 minus the pH of the solution at equilibrium. Because we assume you mixed the solution, right? So if everything's thoroughly mixed, put your phone away. So the equilibrium concentration for the hydroxide ion produced, the base, is 0.00631 molarity. Then you definitely would have set up an ice table. Okay, so you were given KB. They gave you KB. That's really nice of them. So you would have set it up as, oh gee willikers, ethyl. So I'm just going to do ethyl. Okay, and H2O hydrolysis reaction in an equilibrium with protonated ethyl. okay, and hydroxide ion. Ice table. We are told that at equilibrium, we have 0.00631. That's what we found out. Oh my God. Okay, which means we have a change of 0.00631, which assuming that, you know, I started off with no ions and just initial molarity of some value X, okay, we can figure out the change stoichiometrically. So I'm going to also get an addition of 0.00631, okay? And I'm that means going to leave me with an equilibrium value for the concentration of protonated ethylamine at 0.00631. And then that means stoichiometrically speaking, I'm going to lose that amount in concentration of my original base. Okay, that's been transformed now, okay, to 0.00631. So X minus 0.00631. And I can't assume negligible because I just don't know the initial concentration. So I can't assume that it's 1,000 times greater than my KB. So then what I do is I plug it into my KB.
It's 10 to the negative pH.
Yeah, 10 to raise to the negative POH.
Wait, I took the negative log of 2.2.
Oh, you took the P, you did PPH. You did double log. You have to anti-log it. Well, not anti-log it. You have to, whatever. You have to anti-undo. You have to undo. So then you get KB is equal to 5.6 times 10 to the negative fourth, which is going to be equal to the two ions expression, right? Products concentration multiplied by one another all over reactant concentration. So it becomes 0.0. Did someone just whisper, I'm scared? No, okay. 0.00631 squared because the two ions happen to be the same concentration all over the reactant concentration, X minus 0.00631. And you would get a value for X is equal, okay, which by the way, this X is the initial concentration of my ethylamine, which is going to be equal to 0.077 molarity. Now, I think it asked you actually what was the mass. So what you got to do is you got to go from the molar concentration to moles to mass. So what you're told is you originally had 0.077 molarity. You were told this was in a solution of 250 milliliters, so times 0.250 liters. So if you wanted to stop it, what you could do is set it equal, say X moles is equal to 0.250 liters, and that would give you some amount in moles. And whatever that amount of moles is, then you would multiply that X value from up here times, okay, X in moles times the molar mass of your ethylamine, which was 45.08 grams per mole of ethylamine. And you would have gotten a mass value of 0.87 grams of ethylamine were required for this reaction or this hydrolysis to get that specific pH. So that's the second type of problem. A little bit more math, because sometimes what we do is we ask you to carry it through another round of calculations that you already know. We just ask you to tack it on. So then the final problem is your dream problem. It's the plug and chug problem. It's, you know, the initial, you know, the equilibrium. You just got to find KB. Okay. So what you do here for this one, and we'll end after this, and you'll warm up with the practice problem tomorrow. This will be your warm up. Okay. What we have here is we're given B initial, base initial, and we're given pH or POH, so equilibrium values. And then we just plug in. So here I have a given amount of 9.90 weak base, okay, in 500 milliliters. That is, by the way, their way of giving me my initial concentration. Because what I do is I say, well, my initial amount of base is equal to moles per liter, which is going to be equal to 9.90 grams times moles per liter molar mass of this hydroxylamine is 33 grams. That gets me to moles per liter. I was told I diluted it into a 500 milliliter sample, which is a 0.500 liter sample, giving me a molarity value initially of 0.600 molarity. That was their way of giving you the initial. Is they told you all the individual parts that you then calculated into one actual value that you can use. Okay. Which is, by the way, math from unit 1, basically. Math from unit 1 and 2 is just asking you to recognize it in this context.
You said 33 grams is the molar.
33 grams is the molar mass of hydroxylamine. So then what we do is we're also told the pH at equilibrium. It's found to be 9.904. So if I have the pH, I can find for POH, which is equal to 14 minus pH, which is equal to 14 minus 9.904, which is equal to 4.096, which tells me, by the way, now I can work backwards and say, oh, well, if I know the pOH of the solution once mixed, then I also know the concentration of my base hydroxide ion at equilibrium, given that it's going to be 10 raised to the negative pOH. So then it's going to become 10 raised to the negative 4.096, which is going to be equal to a concentration at equilibrium for my hydroxide ion of 8.0168 times 10 to the negative 5th molarity. Now I set up my ice table. So this was a unique problem because it involved a lot of pre-calculations. That would be a standard long FRQ, but that would be like 3 parts, A, B, and C. Like that would be like a several amount of those parts where you would earn like 3 to 4 out of the 10 points for a long FRQ. Okay. And then what you do is you set up your ice table. So we say we have, I'm just going to do amine. I'm just going to write AM for right now to shorthand it, plus water and in equilibrium with protonated amine group and OH minus producing. Ice table it. Your hand probably is hurting by now. I do apologize. And I have my initial 0.600. I have my final, which is 8.0168 times 10 to the 5th, which by the way is going to be also everything else, 8.0168 times 10 to the negative 5th, because I'm in a 1-to-1 ratio with all of this. Only 1 proton is being exchanged and 1 hydroxide produced. Okay. And then I get that my change would also be minus 8.0168 times 10 to the negative 5th. Positive. Okay. Right. Look down below. And I get that my equilibrium value for my original weak base is 0.6 minus that 8.0168 times 10 to the negative 5th, which is very small. So it basically becomes 0.59 repeating. Okay. So then what you say is it's almost negligible. Okay. What you say then is, what is the KB? Well, you just plug into the KB expression. My 2 ion concentrations multiplied by one another at equilibrium. So 8.0168 times 10 to the negative 5th squared all over my original base concentration at equilibrium, 0.59 on repeat. And I get a value then for KB of 1.07 times 10 to the negative 8th. No units. And if I wanted to have you take it a step further, you could find Ka by doing Kw divided by Kb. And you could find the Ka for this hydroxylamine. What is its acidic equilibrium value if it were to act like the acid? It's a lot, but it's also repetitive math. So if you understand the math in the equilibrium problems, you can understand it in all contexts with a couple small tweaks. Yes.
Later on, will the ice tables get more complicated?
Yes, we will add on another type of table known as ICF.
Okay, so it's like every time you just get squared over.
They will when we have to talk about polyprotic. All right, so tomorrow you'll warm up with this problem. Tonight, because I pushed back things today because I got a day behind, you're gonna also watch a titration video. And then tomorrow I will show you an example of titration and we'll get into full calculations of titration curves at each point in the curve of a titration, of each point in the neutralization process. We can calculate the ions present at each moment. So good job, you guys. I know it's a lot.